All right, we're still working with planes. But before we get back into planes, I want you to remember this part. We talked about this a while back when we were looking at equations of lines. So and it was a small detail that we talked about. We said the scalar equation for a line, and remember, to do a scalar equation for a line, it could only be in 2 dimensions. So this was called our scalar form or our standard form right here. And the thing that we noticed, and if you don't remember, just take a look back, the thing that we noticed was that the vector AB, which was those 2 numbers there, so we're talking about the vector 3 minus 4, that was always going to be perpendicular to our line. So that was a neat thing that we noticed back then. What I'm wondering is it possible to have a scalar equation of a plane? So we had a scalar equation of a line in 2 dimensions, because in 2 dimensions we had 2 variables, we had x and y. So a plane, we're in 3 dimensions now. Is it possible to just add in a z? Can we do something that actually looks pretty similar to the line? It turns out we can. Now technically the title of section 8.3 is called Properties of Planes, but really what we're looking at is a different way of being able to write the equation of a plane. We want to be able to try and just write it in a different way. All we've got to work with so far was that vector equation. And remember, the vector equation had 2 parameters in it, or 2 parameters and our x, y, and z value. 2 direction vectors, 1 fixed point. There's a lot of information required to write the equation of a plane. So what we're wondering here is if there's another way to do it. It says we can describe planes in 3 dimensions using a fixed point on the plane and 2 non-collinear vectors. That's what we did before. The other way to do it, we still need a fixed point. So we need to know a point on the plane. Right? There's no way around that. But now, instead of knowing 2 direction vectors, what we're going to give is a normal vector instead. So a normal vector is a vector that's perpendicular to the plane. So that's sort of our scenario there. We're looking at our point P, and we'd know the values of P1, P2, and P3. Right? That's a point that we would know on the plane. And now we'd have to know the normal vector instead. We need to know the values of A, B, and C. So we're going to give this a shot. Remember, the way an equation works, the equation of anything is designed so that we can find a point that we don't know, right? It's trying to come up with some relationship between x, y, and z of some other point that will satisfy the equation. So here's what we're looking at. There's point P and vector n again. Remember, I'm saying point P is going to be a value that we know. So we know a point on the plane, and we also know the normal vector. Okay, we have to know the value of capital A, capital B, and capital C. Okay, we're going to know that. And what we're trying to do is we're trying to come up with an expression to get x, y, and z. Well, the way that we're going to be able to do that is if point Q is some other point on the plane, then if I draw a vector from P to Q, that's now a vector that's on the plane or parallel to the plane, and the normal vector is perpendicular to the plane. So the vector PQ and vector n have to be perpendicular, and if things are perpendicular, that means that their dot product has to be 0. And basically that creates an equation for us. So what we're going to try and do, I'm going to do, on this slide, I'm just going to do everything in general. We're going to use the P1s, P2s, P3s, X, Y, Z, A, B, C, and write an equation down for this. Then we're going to sort of go back and put some numbers in. What I need you to remember though, again, P1, P2, and P3 are all numbers that we would know, right? That's a point that we were given. A, B, C, and the normal vector, those are all numbers that we would be given. The only thing that we don't know, the only thing that I'm saying are definitely variables, are x, y, and z. The other letters there are behaving as constants. So I need to know this first. I need to know what PQ is. So the vector PQ, we've talked about a couple ways of calculating vectors like this, right? We talked about how you actually move, or the other way you do it is you take the second value and subtract the first. So we're going to get vector PQ, you take the x coordinate of Q and subtract the x coordinate of P. So x minus P1, y minus P2, and z minus P3. That's what PQ is equal to. Let me slide that down there. So I'm going to go to this guy, pq dot vector n, and that means that x minus p1, y minus p2, z minus p3 dot abc has to be 0. Right? Dot product is 0 if you have our two perpendicular vectors. There's our equation. Now I need to multiply it a little bit. It's going to be a times x minus p1 plus b y minus p2 c, and that's all equal to 0. I'll expand. I'm a little short on space. Sorry about that. And I'm going to regroup a little bit. I'm just going to reorganize. I'm going to pull the x first, so ax plus by plus cz, and put those there first. Remember, I said a, b, and c was the normal vector, right? So we know those three numbers. We know what a, b, and c would be. They're just numbers. X, y, and z we don't. Right? They're our variables. The other part that I have still is the a times p1 minus b times p2 minus c times p3, and that's equal to 0. But all of that part at the end, I know everything there. Right? We said we'd know numbers for a, b, and c, and we know numbers for p1, p2, and p3. So that's just a big number, which we tend to call d. So there's a really ugly looking equation, and it's not going to be that ugly. It's actually going to be really nice for us. But what I want to see is that if we set things up this way, all of those numbers are achievable. The other thing I want you to notice is compare what we were talking about a minute ago in that little warm-up. There we go. That was our scalar form, right? The 3 and the 4, excuse me, the 3 and the minus 4 were perpendicular to the line. Well, now that I have this plane, it starts ax plus by plus cz, and a, b, and c were the normal vector again, right? So a, b, and c is perpendicular to the plane. So it's set up in almost exactly the same way it was before. So here's the official thing then. The scalar equation of a plane. It says given a fixed point p and a normal vector n, the scalar equation of the plane is, it's just ax plus by plus cz plus d. So the a, b, and c are easy. That's just the normal vector. The way we get the way we get the value of d is by doing that little calculation there, the minus a times p1 minus b times p2 minus c times p3. Good news. We're going to love the scalar equation of a plane. Okay, it has no parameters at all. That's going to make things a lot easier. The other thing that should be concerning you a little bit, but that we don't talk about it, that d value isn't something we're going to have to remember. Okay, it looks like it's going to be tricky. Looks like we're going to have to do that big calculation, but we won't. It's actually going to be really easy to calculate the value of d. So we'll give it a shot right here. It says determine the scalar equation of a plane containing the point p and the normal vector 5, 1, minus 4. So we're trying to get ax plus by plus cz plus d equals 0. The a, b, and the c just come from the normal vector. So I can start by just going 5x plus y plus 1y minus 4z plus e equals 0. I don't know the d yet. So what we could do is we could back up to that last slide and do that fancy formula and figure out what d is. The clever way to do it, if I know the point p is a point on this plane, then it has to satisfy the equation. So if I just sub that point in for x, y, and for z, I can just solve for d. So we get 5 times 2 plus minus 3 minus 4 times 7. and I can even show it, I suppose, a little bit better. I'm not gonna bother simplifying just yet. I'm gonna move all of those things to the other side of the equation. So minus times 2. It's gonna be a plus minus 3. I'm gonna write it this way, which is gonna look a little bit funny. It'll be minus 1 times, and then plus 4 times 7. And that's the formula that we just wrote down. D equals minus A times P1 minus B times P2 minus B times 3.
Please go to room 185.
So instead of having to remember the formula just by subbing in that point, we get it anyway.
Mr. Go to room 185, please.
And now we'll just simplify. What's that, 321? So there's our, now we have our equation. Therefore, 5x plus y minus 4z plus 21 equals 0. Sorry, smartboard's not working so good. So we have our equation, and it's going to be much nicer to use this equation just for managing to get rid of all of those parameters. Okay, so we're going to try some examples with this. It says consider the plane. Hopefully that plane looks familiar. That's the same, exactly the same equation that we used last class and answered a whole bunch of questions based on it. We're going to try and answer a lot of the same questions today. Determine the scalar equation of the plane. Well, the scalar equation of the plane looks like this. We point on the plane, which we do know, there's a point 423. So we also need to get the normal vector. We can get the normal vector by doing the cross product of two direction vectors, right? Here's D1, here's D2. If those are both direction vectors of the, then their cross product would have to produce a normal vector. So that's going to turn out to be, I've got no zeros. I'm going to have to be careful with this again, aren't I? Cross product minus 1 minus 6, and then a 12 minus 3. Sorry, I'm just double checking that in my head, making sure I got that right. I hope it's right. I think it's okay. So our A, B, and C values. So I got a minus 10x, 7y, plus 9z, plus d. And I'm going to sub in that 0.423. So minus 10 times 4. And then what does that turn out to be? So, it's minus 27 on this side. So d is just 27. So our equation is minus 10x minus 7y plus 9z plus 27 equals 0. Or equivalently, if you wanted to, and it's not a terrible idea, you could just change the sign on everything. It's not really that necessary here, but often you'll see it with the x value written as positive. So if you see that, sometimes we'll make that little change. Okay, that's not a small amount of work. We had to do a little bit there to come up with that new equation. So we'll deal with it now. But I'm not taking for granted the fact that that takes a little bit of work to make the change from the vector form into the scalar form. But here's where it pays off. Here's our equation again, the 10x. I'm using the changed one. It doesn't matter, you get the same answers no matter what you use. minus 9z minus 27 equals 0. If I want to find the z-intercept of the plane, remember the way we did this last day, we wrote everything in parametric form, set x and y to 0, solved the parametric equations for the two parameters, our r and t, and then subbed them back in to solve for z. That was what we had to do to get the z-intercept this time. This time, if we want to find the z-intercept, we set x to 0, we set y to 0, and we solve. And those first two just disappear. So we get minus 9z equals 27, and z equals minus 3. And I'm probably even showing more steps than we need to. Right? So that takes 15 seconds now to get that z-intercept. Whereas yesterday, when we did that problem, you had to do a complete substitution problem or elimination problem using those parametric equations, and then still sub it back in again. Then we did this one. Is the point 22 minus 25, 7 a point on the plane? And to do that, what we did was we picked two of the values, subbed them in for x and y, solved the parametric equations to find our two variables, our two parameters, and then subbed them back in and checked to see if z really was equal to 7. Well, this time what we're going to do is we're going to sub in each of the values. And we're just wondering if it actually equals 0. So if we just plug that into the calculator, 10 times 22, 7 times minus 25, I think I get minus 245, which doesn't usually equal 0, and therefore our conclusion is not on the plane. It's a little bit easier, right? It's a heck of a lot easier than doing all the stuff we did the other day with the vector equation. D. I can't remember if we did this one or not. Is the vector 155 parallel to the plane? So I'm just going to get rid of these guys. Is the vector 155 parallel to the plane? This is an easy question too. We're wondering about the vector 155. What we know about the plane is we know the normal vector. The normal vector is 10 plus 7. 10, 7, minus 9. That's the normal vector. Well, if 155 is parallel to the plane, then it would have to be perpendicular to the normal vector. Right? You should be able to picture that. If 155 is parallel to the plane, or you could picture it almost sitting on the plane, the normal vector should be perpendicular. So is that vector perpendicular to 10, 7, minus 9? And the way you check that is you do the dot product. And what do we get? We get, oh, we did do this question, didn't we? I remember it working out so nicely. Minus 45, we get an answer of 0. Therefore, 155 is perpendicular to the normal vector, so it's parallel to the plane. Saying therefore so doesn't make sense. So therefore, the vector is so that's not too bad. That was one of the ones where I said you just had to think about what you needed to do to actually answer the question, right? Okay, here's our last one. Let me get rid of these guys again. Go away. Go away. This question we didn't do before. That's our new one. Determine the equation of a plane that's parallel to, there's my equation again. I've got it, I don't know why I did that, but I've got it flipped around. I've got the negative back in. That's okay. Determine an equation of a plane that's parallel to the plane we're dealing with, but now it has a y-intercept of 5. So what does that mean if planes are going to be parallel to each other? Well, if planes are parallel, if we're thinking about how we did it last day, that means that the direction vectors would be the same, and we need a new point, right? We need our new fixed point. We still have a new fixed point. It's here. If it's giving us a y-intercept, that's just a fancy way of giving us another point. But we have our scalar equation this time, right? That just means that the normal vector that we were given here is the same normal vector of our new plane. If two planes are parallel, they just have the same normal vector, right? It's easy to picture. Just think of the floor and the ceiling. Your normal vector would be a vector going straight up or straight down. It's a normal vector to both the floor and the ceiling. It should work for both. So I'm going to say if the planes are parallel, they just have the same normal vector. But the d value is going to be different. So what we need to do is we're going to set, I'll use this minus 1 again just for kicks. Minus 10 minus 7y plus 9z. But now it's d. I don't know what that d is going to be for this new one. This new equation now doesn't have to have that old point, whatever it was. It now has to have 0, 5, 0 as a point. So I just sub that in instead and solve for our new d value. Which actually turns out really nicely because I'm subbing in so many zeros, right? D is just 35. So the parallel plane is minus 10x minus 7y 9z plus 35 equals 0. And what you'll notice is anytime I want to change, anytime I want to have parallel planes, all that happens is we change that number right there. Right, the normal vector stays the same, or potentially the normal vector could get multiplied by something, right? I could switch it back and do that positive 10x, positive 7 minus z. I could multiply that normal vector by 17 if I wanted to. I'm not sure why we would. But those are all different ways of creating the same plane. What I want you to notice out of this one then is how much easier it was to do these calculations with this scalar form. Right? Vector form works great. It's very valuable. I don't want you to forget it. We're going to need it. But if we're going to do calculations, calculations are much, much easier with this scalar form or standard form than they were with vector form. One thing that's interesting, you'll try a couple questions, I think, today, where it's going to say determine the equation of the plane. If I ever ask a question that just says determine the equation of the plane, you have two options now. You could give me the equation in scalar form, this form, or you could give it to me in vector form. And depending on the information that you're given, maybe one way is easier than the other. So just think it through and try and think of what form might be easier. That may mean that your answer is different from the answer in the back of the textbook, but that's okay. Right? Think about what would be easier for you to do and try and take advantage of the different properties that the two types of equations offer.